Welcome everybody to the May 2024 Raleigh Astronomy Club indoor meeting. Any new members in the audience today? Nobody. On Zoom? I can't see if you raise your hand on Zoom, so sorry, but
I guess I'm a
yeah, well,
guest. I'm a guest on the Zoom from
so
Wisconsin.
yes, okay. Ron, do you want questions while presenting or at the end? I forgot to ask. At the end? Okay, so tonight, please, for our presentation, be respectful. Hold your questions to the end. We'll have this microphone, assuming the battery doesn't die, to come around so you can ask the question so it's audible to everybody on Zoom. So safety, so room hazards. We have some cables behind the projector. Please don't trip and die. Watch out for bags next to chairs. It's not very bright in here. So there's a big table in the front. This is the dimmest area. Big table, don't hit it. Anybody CPR certified in the room today? One person, okay, thank you. Your services, I hope, will not be called on, but emergency caller. Dana, you want to take that one? Yep, okay. Fire equipment, we've got a fire extinguisher near the door in the back. And I think that's it. Fire switch by the chairs. Don't hit that unless it's an actual fire. And then remote attendees, please be aware of your own surroundings. There's exits out of this room. So the green is where we are. And there's an exit for the side there, I think. And then there's an exit out that way. Again, all this stuff, hopefully we will never, ever have to use, but it's good to know. Okay, before we get into the meeting, upcoming events in June and in the beginning of July. We've got First Fridays with PLC out at Creedmoor on the 7th of June, Willard on the 19th, Astronomy on Tap on the 29th, and then First Fridays with TLC again in July on the 5th. Of course, those are the First Fridays. There's a nice report with all of these and more details on the RAC website. I know nobody's going to be able to type out that URL, but go to the website and search for Outreach Committee report. So after the meeting, we'll, if there's enough people, planning to go to Sammy's, hang out, dinner, dessert, drink. Anybody thinking of going tonight? 1, 2, 3. Okay, so it looks like we have several people. Wonderful. All right. So our presentation tonight. We have Mr. Ron Monti. He's a member of the Raleigh Astronomy Club since 2012. In 2023, he received the Astronomical League Master Level Outreach Award. He's a science instructor at the Osher Lifelong Learning Institute at NC State University, where he received their Volunteer of the Year Award in 2018. He's also a volunteer educator and exhibitor at the North Carolina Museum of Natural Sciences. And today he's going to wow us with how to catch a gravitational wave. Welcome, Ron.
Just to, the reason I was got interested in gravitational waves was because about, I don't know, 10 years ago, 8 years ago, on the Friday before astronomy days, we had a speaker come in who was an engineer who worked on LIGO, which is the Laser Interferometry Gravitational Observatory. And he was telling us about the amazing engineering involved with this project. And I had never heard of it before at the time. And you don't read about it very much in anything that's geared towards the general public. And even for the scientifically oriented public, you don't see too much about it. But gravitational waves will definitely challenge your understanding of scale. And this is Gail Jones. She's a professor of education at NC State University. And she and her colleagues wrote this book, Extreme Science from Nano to Galactic. And it's all about scale and the importance of understanding scale. And she had this to say about understanding scale. An understanding of scale and scaling is of central importance to a scientific understanding of the world. And though scale has always been central in science, an argument can be made that it has never been more important than it is right now. And that's very true, at least from my perspective, that I can understand it a lot better by trying to use different cognitive tools to help understand the scaling. And it's interesting because Gail also showed up at a RAC meeting about, this is going back even farther, maybe 12 years ago or 14. And she was not here to talk about scale or scaling. She came to hand out a survey to club members asking us about retirement. She was conducting a survey and a study on how retired people spend their time. So she thought that the people involved in astronomy would be a great place to start. So yeah, so I never found out, what the results of that study were. I don't, maybe she didn't want to tell us, but so now this is an overview what we'll talk about. What is a gravitational wave? The scale of gravitational waves, the physics and engineering of LIGO. And this is a view of LIGO. I believe this is the one in Italy. And I'm not sure the length of these arms that contain the laser beams that are bounced back and forth, but the ones in the US are like 2.5 miles long. And I'll get into a lot more into the description of how this facility works. And then the last thing is future research. So what are gravitational waves? Gravitational waves are ripples in space-time. That's waves released by the conversion of a tremendous amount of matter into energy. So it's kind of like ripples in a pond if you throw a rock into a pond. And it's similar in more ways than one, because like if you throw a rock into the water, the waves that are closer in are shorter and the wavelengths that are farther out are longer, which is kind of like the sources of gravitational waves in the universe. And of course, the waves from gravitational waves expand in all directions. And here's, the famous equation, converting energy from matter into energy. And these gravitational waves are caused by cataclysmic events, such as, and this list that you're going to see is ascending order. So the lowest magnitude will be the first item. So the spinning of a neutron star, and the next highest, largest kind is collision of two neutron stars. And then the third is a black hole tearing apart a neutron star. And I guess I don't have to explain, like about neutron stars or black holes, but, I think just a quick explanation is that if you have a star that's burning through all its the fusion processes, and it goes through hydrogen, helium, oxygen, nitrogen, all the way up until it starts burning iron. When it reaches iron, it can't fuse iron anymore because it takes more energy to fuse the iron than the fusion gives off. So as a result, the star can't hold up against the gravity pulling in, the gravitational force pulling in on that star. So the star collapses. And if the star is greater than 30 solar masses, it results in a supernova. And if the supernova after the supernova occurs, if the remaining core of that star is more than 3 solar masses, it results in a black hole. If it's less than 3 masses, it results in a neutron star. And I don't see Steve waving at me, so so the next one is a collision of 2 black holes and a collision of 2 supermassive black holes. And there's an important distinction here, mostly from a technical point of view as to how they are detected. And then the largest thing that would cause gravitational waves are cosmic strings. And cosmic strings were supposedly created at the Big Bang and can still be seen in the universe, and they give off gravitational waves. So this is just a brief video, a simulation of what the collision of 2 black holes might look like. And then this is a simulation. When these black holes collide, right before they collide, they're going something like 2/3 of the speed of light. So that's pretty doggone fast for something so massive. So the significance of detecting these gravitational waves, why is it so important? Well, they're a whole new way of discovering the universe. They're not electromagnetic waves, such as telescopes. So here's the electromagnetic spectrum here. And almost all of what we know about the universe is via the electromagnetic spectrum. And there are different types of telescopes to view the electromagnetic spectrum. And you have the visible light telescopes, and then you have the microwave telescopes here. And this is the ALMA telescope in Chile. And then you have like the James Webb telescope, which is in the infrared over here. So they have others too, like there are gamma ray detectors and telescopes that they have as well, and radio telescopes. And gravitational waves are not particles. So the particles that we can examine that are coming from outer space are cosmic rays and neutrinos. And the cosmic rays are alpha particles, which are 2 protons and 2 neutrons, and beta particles, which are just electrons. It's just a different name for the electrons. And this is a cosmic ray detector. It's in Argentina. And there's an array of like hundreds of these things down there, and they're filled with water. And they detect these cosmic rays as they're coming in, mostly from outside our solar system or even from the sun. And then there's neutrinos, which they have these large underground vats containing exotic chemical solutions in there, like some include like even cleaning fluid. But you can see how big this thing is. It's a vat, and that's a canoe with 2 researchers in it there. And if a neutrino hits one of the molecules, the active molecules in the solution here, it gives off a beam of light, a spark of light, and these detectors around the outside of it will detect those. So gravitational waves are not either one of those 2 types of things that we know about from in the universe. Gravitational waves can detect some things that we can't otherwise see, such as the collision of black holes. And why can't we see things like the collision of black holes? Why would you think? Yeah, that's a question.
No light comes from it.
A lot of times they're just so far away it can be impossible to resolve, but also things in the obscuring the view of such black holes or whatever, star, we could barely even see the center of our own, galaxy, right?
Yeah, yeah. Well, actually, it's because nothing can escape the gravitational pull of a black hole, not even light. Yeah, yeah. So how would we know if something like this happened? And the particles like the cosmic rays and the neutrinos wouldn't be able to escape either. So there's no way we would know what was happening out there. Oh, oh, yeah. Oh, okay. Okay. Thank you. So now it's kind of important. It's kind of important that we understand the scale of gravitational waves. And this is a website that every astronomy days we have as one of RAC's displays is Scales of the Universe, where we have a screen set up showing this app here, Scales of the Universe. And it's a wonderful app. Like I'll show you what it has on there in a minute. But it was developed by 2 high school students. So it's amazing that they were able to do something like this. Now they're probably postdoc, in some university somewhere. Yeah, yeah. So that's at the same scale. These are different objects that are all at the same scale, which is at 10 to the 6.9 over here meters. So this is all expressed in meters. All the objects you see here, you're viewing are 10 to the 6.9 meters.
Although the resolution's not high, read the names.
No, no. So this is the name of the website that you can go on and look at this. And here's one of the screens. Now this is at 10 to the 9.7 meters. And you can see here is a carbon atom, and this is a water molecule. Now this doesn't have to do with the gravitational wave itself, but it's just to give you an idea of the scale that we're going to be watching. So now you see a carbon atom is at 10 to the minus 9.7. And here's the one we just saw, 10 to the 6.9. And now what we're going to do is we're going to try to show you using a proportional analogy how small an atom is. So now if you take the exponents from the atom, which is minus 9.7, and you add the positive 6.9 and divide by 2, you get the average. So here, minus 9.7 plus 6.9, those are the exponents. Divide by 2, it equals minus 1.4. If you go back into the app, you can move this cursor back and forth to different scales. And if you do that, if you look at 10 to the minus 1.4, what do you see? You see an orange. So it's not an orange. I superimpose it here. So because it's easier to visualize. So now from this information here, we can make a proportional analogy or an analogical proportion. So an atom, which is 10 to the minus 9.7, is to an orange, which is 10 to the minus 1.4, as an orange is to the Earth. Now, that it takes a while to let that sink in. Of course, we know how big an orange is, and a lot of us have traveled enough, so we know how huge the Earth is. Okay, so now the ratio of the difference in size between an atom and an orange is the same as the difference in the size of the orange and the Earth. So now here, imagine an orange on the surface of the Earth. So this is taken from a plane flying about 20,000 feet. And you see that tiny little dot there. Imagine that there's a house there, and on the kitchen counter is an orange. And imagine how small it is. The distance from one side of this photo is about 10 miles to the other here. the Earth is about 800 times this distance that you see here. And that would be compared with that orange on the counter of this house here. So that's really amazing. Yeah, yeah. No, I'm not kidding. You can do the math. So the scale of gravitational waves is even more amazing. So here's a proton, and the gravitational waves are 1/1000th of the diameter of a proton. Now that, the proton over here is 10 to the minus 14.8 meters. So now we're going to do an analogical proportion of gravitational waves. So this is what you see on the monitor in the LIGO detector. They detect a gravitational wave, 10 to the minus 18th, is to a human hair, which is 10 to the minus 4th. Yeah, that's a human hair. It's kind of gross. I don't know whose hair it is. As a human hair is to, so now look, this is 10 to the minus 18th, this is 10 to the minus 4th. So we're going to be looking for something that's 14 orders of magnitude difference here. So it would be something that would be 10 to the 10th. That's 14 orders of magnitude down here. So what's at that size and that we can find? And it turns out it's the star Pollux. And just to give you an idea, there's our sun. Pollux is 10 times the diameter of our sun. And our sun is 100 times the diameter of Earth. So now you can see how amazingly small this is. So the ratio, the difference in size between the gravitational wave and a human hair is the same as the difference in size between the human hair and the star Pollux. That is huge. I mean, you can, even using all the cognitive tools that we could use, it's still, like just boggles the imagination. So, but there is a technical term to explain this difference in size. So, I think they use this cow at the dairy where I get my milk. Yeah. So now, how can the LIGO detector detect something that's so small? So again, the name of it is the Laser Interferometer Gravitational Wave Observatory. And it's capable of the smallest measurements ever made. And there's two in the United States. One is at Livingston, Louisiana. Has anybody ever been to any of the LIGO detectors? No. I know some people who have been, and they have tours there you can take that are very interesting. So here, these arms are like 2.5 miles long here. And the laser beam that's generated is inside the structure here. And the beams go, there's a signal splitter that splits a single laser beam into two parts that go down each of these arms. And I'll talk more about that in a few minutes. So here's the one in Louisiana, and here's the one in Hanford, Washington. And they have to be a couple of thousand miles apart because, as you'll find out, it's very important to kind of make sure that what you're detecting is really a gravitational wave. So these are the three scientists that won the 2017 Nobel Prize in Physics. And the three people are Rainer Weiss from MIT, Kip Thorne of Caltech, and Barry Barish. Now, Rainer was one of the first people who suggested, that we should try to measure the gravitational waves. Kip Thorne was the one who provided a lot of the scientific knowledge to be able to do that. And Barry Barish was one of the ones who was responsible for getting the LIGO detector actually constructed. And Steve has a picture of himself standing next to Kip Thorne here, who's a friend of his. So you might want to check in with Steve after the presentation. So the important thing that we used to measure these things was interferometry. So what is interferometry? LIGO uses the interference between two halves of a split laser beam to measure incredibly small distances. So now here are two wavelengths of light. And so the wavelength goes from left to right and the amplitude is up and down here. If you added these two wavelengths of light together, you would get a beam of light with an amplitude that's twice as high as either one of these. And that's because here, the high point of this wavelength gets added to the high point of this wavelength, and the low point here gets added to this low point. So here's the sum of the two high points and the sum of the two low points. Now, what happens if you shift one of these two by half of a wavelength? So here we have that. So the one on bottom is shifted to the right by half a wavelength. Now, if you try to add them together, the high point on this one matches up with the low point on this one, and the low point on this one matches up with the high point on this. They negate each other. They completely block. They turn, there's no wavelength that results from this. So you get a completely flat line here. And the if you're trying to measure it, there's no light there. It's completely black. It's almost like if we're using sound canceling headphones, the sound canceling headphones shift like a half a wavelength on the incoming sound, and you wind up not hearing anything. So I'm going to show you a video. The video doesn't have any narration, so I'm going to just show you some screenshots from the video and explain what you're going to see as best I can. So here you have a laser, and it's shining a beam of light to a signal splitter. And the signal splitter breaks that beam of light into two equal parts. Part of it is reflected down one of those long arms you saw in the photo of the LIGO detector, goes down and hits a mirror and comes back. And the other one goes straight through, hits another mirror and comes back. And in the LIGO detector, these beams bounce back and forth about 400 times, and then they get recombined here. The signal splitter can recombine those two beams into a single beam again and shine them on a detector over here. Now, when a gravitational wave, if it should hit the LIGO detector, it's not going to affect the beam on the left-hand side very much because it's coming down lengthwise, and it doesn't affect it too much. But for the one on the right, the beam on the right, the gravitational waves are going to hit it broadside. And so the ripples in space-time are going to contort the length of this beam of light going back and forth here. And that difference in size, like we were talking about, the gravitational wave is only 10 to the minus 15th meters, something like that. It's going to be very, very small, but yet it's going to get recombined here, and that beam is going to hit the detector. So now here's the two arms with the wavelengths going back and forth. And when they recombine here in this particular photo, what do you see here? You can see the beam from one light beam is exactly offsetting the one from the other. So they're not going to see anything on this detector. And that's the way they want it. Most of the time, this detector is in this mode here where they're not going to see anything. So they know that if they do see something, that means a gravitational wave could have hit the detector and caused some patterns to appear on the detector. So now here's where they don't see anything. This is the steady state of the LIGO detector, where it's not showing anything on the screen. These light beams are canceling each other out. That's the way they set it up to work. Now here, if a gravitational wave or some other disturbance hits the detector, it offsets those light beams. And now over here, you see something on the screen, just like we saw in that display of how the waves can combine to make a new wavelength, a new larger wavelength. So this is not from the LIGO detector, but it's just to give you an idea of something like they might see there. So now this is the video, and the beams are hitting the signal splitter, and you can see how the mirrors are moving back and forth and causing the detector to pick up a signal. So it's going down to one of the mirrors, coming back, getting recombined at the signal splitter. Now there should be nothing on the detector. And now there should be something, as you see the wavelength is changing because something disturbed one of those arms, and it's causing the pattern on the detector. This is an ingenious way that they developed to detect these gravitational waves. And Steve was showing me a book that they had come out with some theories about how to do this back in, was it 1942? Yeah. So now here's the steady state again. The laser beams bounce back and forth 400 times before being combined and sent to the detector. And like I said, the base state of the LIGO is the half wave, no light state. Now, this is going to go into the engineering of the LIGO. The lasers, LIGO uses the interference between the two halves of a split laser beam. And the wavelength of the laser beam is 10 to the -6 meters. But gravitational waves are 10 to the -18th. So how can you measure something that's 10 to the -18th if you have a wavelength that's 10 to the -6th? Well, here it turns out that you don't need to offset this by a complete wave. It only takes a minute amount of offset to produce an image on the detector. And that offset can be down to 1/1,000,000th of a wavelength, and it'll still produce an image on that screen. So if you add 1/1,000,000th, which is what, 12 to the 6 up here, that gets you down to the -18. So maintaining the stability and purity of the laser beam is one of LIGO's biggest challenges. And a key component of besides having they have ways to ramp up the laser beams and to purify the signal of the laser beams before they input them into the signal splitter. And then the mirrors that the beams bounce off of, they're like 13.4 inches wide and weigh about 88 pounds. And here's two of them. There are actually 4 in the LIGO detector because each arm is bouncing the beam back and forth, up to 400 times. And here are 2 techs looking at the mirror as it's installed in the detector. And this is the housing that the mirror fits into. And this is the mirror down here. This other one that looks like a mirror up here is actually a counterweight. There's a technical name for it, but counterweight works better for me. And it's made of ultra pure fused silica laid down in nanometer thick layers and polished to within several atom widths of theoretical perfection. They're the smoothest mirrors ever created. And here you can see a tech looking through the mirror, what it looks like. The highly reflective surface absorbs only 1 in 5 million photons in order to avoid heat buildup, which could distort the surface. When you're talking about these gravitational waves that are 10 to the -18th, you really need to have everything working perfectly to see them accurately. The mirrors help keep the laser beam focused. They're slightly curved to help focus the light, the laser beam as it bounces back and forth. Now the vacuum tubes are 2.5 miles long, and they have to be adjusted by 1 meter for the curvature of the Earth. So if you go from one end to the other, you measure their distance off the ground, one end is going to be like 1 meter higher than the other. So this is the Livingston one. So this down here, this end here is like 1 meter higher off the ground than the mirror down here. And this is what you see from the air, like in the prior picture. This is the outside of those arms, and that's what you see from the outside. But the inside contains these tubes that the laser beams goes down through, these vacuum tubes. And these vacuum tubes are the second largest ultra-high vacuums in the world. The largest is in the Large Hadron Collider in Switzerland, and they can get the vacuum down to 1/1,000,000th of an atmosphere, which, there's a whole process that they have to go through, that they have to heat up the air inside and use special jet type vacuum. They're like vacuum cleaners that pull the air out of these vacuum tubes. They have to run them for like 3 days, 4 days before they can get them down to 1/1,000,000th of an atmosphere. The reinforced steel tubes are about 4 feet in diameter, and the metal that surrounds the tube is about 1/8 of an inch thick. So here's the tube. You can see this welder here, and actually the atmospheric pressure at sea level is about 15 pounds it's 1 ton per square foot. It's about 1 ton per square foot is the atmospheric pressure. And so on the inside, that has to hold up for every foot of here, it has to hold up to about 2,000 pounds. And actually 1/8 of an inch thickness of these tubes is not enough to be strong enough to do that. They would be crushed by the Earth's atmospheric pressure. So they weld these rings around the outside here to reinforce it, to be able to, sustain that pressure. The vacuum tubes also prevent the refraction of laser light by moisture and particles, because even like a mote of dust on hitting the mirrors or something, or any moisture particles in the air, or even molecules in the air, could affect the measurements. They also prevent sound waves from disturbing the mirrors. So vibration is another major concern for the detectors, because anything like a truck driving down a highway nearby, or some of the staff members walking in a hallway near the detector, or a plane flying overhead, things like an earthquake on the other side of the Earth, or a storm, 1,000 miles away, could affect the measurements of these gravitational waves. But there are different methods that they use to control that. And the first one is, at such small scale, like that's what I just talked about, but there's an active vibration damping system. And they use sensors and motors that work like sound canceling headphones. And this is a picture of one of them. And it's got these sensors in it that detect vibrations in the ground, and has motors that compensate and offset that vibration to zero it out, like that sound canceling headphones. I'm not sure of how many they have at the LIGO detector or where they're placed. I think they would have to at least have one under each of the 4 mirrors. Then there's a passive vibration damping system, which is the quadruple pendulum that isolates the mirrors from the outside vibrations. And this is what it looks like. I showed a picture of this before, and here's the mirror down here. And this is a sketch of what that is. And there's 4 levels to it. You can see this is the first level here, these wires coming down from this, these cross supports holding up this. Then there's another pendulum here. This is the first and second here. So that's 2 sets of pendulums. Then a third one here, and there are beams or cords holding up each of these. And then the 4th one down here that actually attached the mirror. And the mirrors are so sensitive, they couldn't use just anything to attach to the mirror. They had to fuse the same type of material that the mirrors are made of onto it. So these cords here are made of the same silicon as the mirror, and they were fused onto it to prevent resonance in the mirror that could distort the gravitational waves. And then there's another reaction mass behind the mirror here to further dampen any vibrations. And this is just a view of the inside of the top of that housing for the mirror, some of the gear inside there. So the vacuum tubes also prevent sound waves from disturbing LIGO's mirrors. And then that was the local vibration control. Then they have kind of a way of global vibration control, which is that they measure the gravitational waves from one location against the waves received at another location. So like if Livingston receives something that looks like a gravitational wave on the detector, they'll contact Hanford and say, well, did you see anything on your detectors? And to make sure whether it was or not. And it could be that, they detected the same earthquake on the other side of the planet, but, they have ways of figuring out if it was or not. And they can, eliminate a lot of those vibrations. If it's a truck or passing by or a plane flying overhead, those can be eliminated right away because it's probably not going to be exactly the same at both locations. But even things like the storms and the seismic activity can be eliminated. And so some of these other detectors around the world, here's the 2 we saw. Then there's another one that's almost as large in Italy. It's called a Virgo detector. There's a smaller one in Germany and another smaller one in Japan. And they're building one that's probably the size of Virgo in India. So now, with the LIGO detector, they can only detect certain gravitational waves. They can only detect the smaller ones. If it's a larger gravitational wave that's caused by a more cataclysmic event, such as the collision of 2 supermassive black holes, the LIGO can't detect it. It also couldn't detect anything like a cosmic string. So they have plans in effect to come out with a larger version of LIGO. And, they already have the LIGOs are already around the world. So to be bigger, they would have to put it into space. So yeah, like the LIGO can detect the waves from the smaller black holes, but not the supermassive ones. So LISA is the laser interferometer space antenna, and it's planned for 2034, so in about 10 years. And this is like an illustration of what it might look like. So here's the satellite, and there's going to be 3 of them, 1, 2, 3, shooting laser beams back and forth between each other. And this is how it's going to follow Earth in Earth's orbit around like this. It's amazing. And I meant to look up to see how far apart they're spaced. I didn't get to do it, but from that illustration, it looks like they're at least, probably 200 or 300,000 miles apart. So these are the laser beams between the satellites. And it's got to be some kind of feat of engineering to, be able to, locate these satellites so precisely, like when it's on the ground. Yes? Oh, so yeah, so that would be about a little over 1,000,000 miles. Okay. So the LISA will also look for waves created by cosmic strings and the Big Bang. So that ought to be very interesting. So the collision of neutron stars. Now, the neutron stars are kind of in the mid-range of different events that cause gravitational waves, but they're very important for LIGO. And why? The LIGO detectors can roughly triangulate the locations of the source of gravitational waves to a region of the sky. So like they can tell by how the gravitational waves, the timing of how they hit the two arms of each detector. And they can also measure between the two LIGO detectors, like in Hanford and Livingston, and triangulate to a region of the sky that it might be in. So when two neutron stars collide, they're not like two black holes. Like when two black holes collide, nothing escapes. You know, the light can't escape, the cosmic particles can't escape. With a neutron star, those light waves can escape, and they can detect them on Earth. So this is a view of the sky here. And here you can see, this is like, I believe this is what something called a Fermi and integral satellites are detecting from neutron star collisions. And you can see it crossing the sky. I think it's because of the orbit of the satellites. They could narrow it down to this location. There's also a ground-based detector of what they're detecting is gamma rays. They're the shortest electromagnetic waves that are coming from these neutron star collisions here. And this is the ground-based one here, and they overlap. And then when they overlap the LIGO detectors here, look what happens. This is probably the point in the sky where that collision occurred, was where the three overlap. So, and why is this important? Because the LIGO detectors will detect the collision, the neutron star collision, before the other satellites can. And so that they'll move the ground-based and orbiting satellites to point to that part of the sky that LIGO is saying that, saying, okay, here, point your telescopes to this area of the sky. So they'll be ready for when that supernova occurs and the neutron star, or rather the two neutron stars collide. So future research, the LIGO detectors, like I said, are a completely new research tool to uncover the nature of our universe. And just as the electromagnetic spectrum provides a tremendously rich source of information, it's almost everything we know about the universe is from the electromagnetic spectrum. And you know, if it comes from a distance, it's from the electromagnetic spectrum. So the gravitational waves will hopefully give us a significantly unique new perspective, and they can provide evidence of the Big Bang, hopefully, or the nature of black holes, maybe, space-time, and possibly even dark matter. So that was the presentation. If you have any questions, I'd be happy to refer them to Steve. Yeah.
My rudimentary understanding of the LHC and the interference pattern that occurs seemed similar to me when you were showing us the detectors and how there was an interference, and then what was showing up on the mirror would change. And I'm curious what the similarities or differences are between gravitational waves and the waves produced by the LHC and what's detected there.
Yeah, the Large Hadron Collider.
Thank you.
I didn't know that, but Steve, are you aware of anything? Yeah, yeah. Mm. Yeah, yeah.
Energy and directions. That they can determine what's been produced in those collisions. So they're really two very different kinds of detection. This doesn't have particle collision. This is just light waves.
Yeah, yeah, yeah. There was another. Oh, there was a question up here. Also.
So when can you hear me through? Yeah. Okay. So when the sensor on the vacuum tubes, when they're affected by gravitational waves, are they measuring changes to the speed of light or the changes in distance, or both?
I believe, I maybe both.
The speed of light doesn't change. They're just getting the intensity of the light that hits the sensors. Okay, and from that they get the signals. If a gravitational wave goes through, then the signal will be of a certain form, and then they record that, and then they have to determine if that form is a gravitational wave or not. And they have done computer simulations with hundreds of thousands of simulations of what happens if, say, 230 mass black holes collide with each other in a certain way and at a certain angle, and that will give a certain signal. And then when they get a signal in the LIGO detectors, both from Hanford and Livingston, then they'll take that signal that they get that looks like gravitational and compare it to the hundreds of thousands of simulations they've got, and that will tell them what they saw. So for example, they'll see 230 mass black holes colliding will give a certain signal, a certain frequency and a certain amplitude and that sort of thing. And then they'll know that that was a gravitational wave from two black holes colliding of that mass in that way. So the numerical relativity that needed to be done to find out what a gravitational wave will look like in a LIGO detector required thousands and thousands of calculations over many years. And the theory behind this is even more complex than the hardware behind it in a lot of ways. So that's Kip Thorne, the guy who was in the middle of that picture, is the guy who looked at the theory behind all of this and how to determine what really a gravitational wave would look like if it hit these detectors.
So the change in intensity picked up by the sensor, isn't that sort of measuring the lack of synchrony between the two waves, right?
Yes.
So what causes the change? Is it because
it's because
the measurement of the length of that?
Yes.
Of the
Basically,
tube
yes.
is effectively different?
Yes. They're only slightly different, like you said, 10,000th of the width of a proton, but they do enough of that to get a signal that makes some sort of sense. And so they designed all this to get rid of all the noise. And then the noise at Hanford is different than the noise at Livingston, is different than the noise in Italy. And so they get these detections, they can get rid of all the noise.
So if this thing picks up a true celestial event, what's the duration of time? Do you have to really be looking at it like, in a few seconds?
Well, they turn them on and they let them run for however length of time they plan to let them run. And then they take all these signals and they send them through the computers and analyze them. And if they get a signal, then they send out a message over the internet. Oh, we found a signal. So they're constantly looking at these signals and they send them out. So you can have an app on your phone that will beep you when they've got a new signal. And then as soon as those signals come through, then all the astronomers that do this multi-messenger kind of astronomy with neutrinos and X-rays and gamma rays and whatnot, they'll say, okay, we think we know there's a gravitational wave, so be prepared to point to either look at the signals you've already gotten, like from neutrinos or something, or look at your X-ray and gamma ray sources and point your telescopes in the right direction. And so gravitational waves will be the trigger for all these other events. We're pointing your telescope at other places, which is remarkable.
Do you get beat when this happens?
Yeah, in fact, I do have that happen.
Oh, questions.
Well, hopefully mine is, well, I don't know. Anyway, what is the purpose of measuring the cosmic strings that for the strings? Like what do you find out when you measure that? I think that is one of the things that is being measured with the LIGO as well.
Well, that would be from the LISA detector, but I believe that it could help prove the Big Bang
Oh, okay.
Hypothesis or theory, and maybe give some input into cosmic inflation and things like that. And my understanding was that these cosmic strings were formed by the rapid expansion of the universe after the Big Bang. So I don't know if you have anything to add.
Well, there's not been any cosmic strings seen yet. So it's purely hypothetical, theoretical, okay, for that. And one of the detectors that you didn't mention was the pulsar arrays that are already being used, because there are pulsars that are similar to LISA, only on a much more gigantic scale, as you have these pulsars that are sitting out in the universe, and they have very specific timings in these pulsars. And as the gravitational wave goes by these pulsars, they move the pulsars a little bit, and that changes the timings that we get of these pulsars. And these pulsar timings are incredibly precise. And so if you have a lot of them, you can look at the timings on each pulsar, and from that you can figure out whether a gravitational wave has gone through. And these are the kind of gravitational waves that are very long wavelength, the kinds of things that Big Bang or the cosmic strings might produce. Okay, so that's what this is. That's the mechanism. It's already in use.
Yeah, well, very interesting.
My question is not scientific. It is who is funding these phenomenal projects? And politically across the earth, are they cooperating together? And politically across the earth, who is funding it in the other countries? This is an immense amount of money. And no one, as you say, talks about it. So, and is it ever made public who is funding these phenomenal projects?
I guess it's ultimately it's the taxpayer, but they're funding research done by, like, Caltech is one of the major institutions, and probably MIT and others. And I don't know if they're raising other funds on their own. Yeah. That's all I have. That's all I have.
Who is funding this?
I can tell you
Yeah.
that.
Yeah.
Job it was to fund LIGO. Okay, and he worked for decades with Congress to get this funding going. The funding for the other projects are the European Space Agency does the one in Italy. The Japanese fund the stuff in Japan. The Indians fund in India. So it's spread out all over the world. If you want to go, you go to the NSF website or go to these websites, you will find exactly who is paying for it, how it's paying for it, who got the grants, when they got the grants. This is all very public information. Always has been, always has to be for legal reasons. So there's no hiding going on in this at all. It's utterly public.
Is there an exchange of information?
Yes,
between these other
absolutely,
countries?
absolutely. They're all work very closely together. They have to, in order to use the data together. So every one of these countries works with every other country, very detailed ways. People from all these countries go to these other countries and work with everybody. It's one of the best international collaborations you can imagine. So it's not, there's nothing hidden by any of this at all. And the technological stuff that's come out of this already has been remarkable in terms of other products that have been created because of the research done here. Both the theoretical research and the experimental research have produced products and services and that themselves produce taxes that go back to these governments. So it's all.
We have questions back here, so you guys can chat after. Dana, is there any questions online too? Okay, well, get the two here.
Yeah, I think my question was pretty similar to this before. So when you talk about the size of the gravitational wave, like 10 to the minus 18 meters, that's really essentially the change in the distance between, the laser path to the, from the detector to the mirror. It's not the wavelength of the gravitational wave, which is probably enormous.
Yeah, that is the gravitational wavelength, 10 to the minus 18th meter.
No.
That's just the effect it has on the protons or on the mirrors when they're being moved.
Yeah.
The wavelength of the gravitational wave is much larger. It's just the effect it has on the apparatus is very, very small.
I'm learning as much as everybody else here.
Rudimentary question and slightly embarrassed, but it made me laugh when you show the image of the triangulation of the lasers in space going around Earth. I thought, are those the Jewish space lasers?
No, that I know.
So online, we were asked, how frequently do these detectors actually catch a gravitational wave?
I believe that the first one that they detected was in 2016 during the trial run. 15. Yeah, during the trial. Yeah.
Hundreds since 2015, just to catch it on the Zoom. Okay. All right, last question. We'll break for the business meeting.
Okay, so how long did it take for them to work out the engineering problems to know that this worked?
Yeah.
The first notion of doing something like this was, oddly enough, in Chapel Hill in 1957. There was a conference of all the people who were doing gravitational research came to Chapel Hill for a conference to decide what to do about working with gravity. Okay, and the top people in the world came to this thing. Okay, and Dick Feynman, you may have heard of, Richard Feynman, and Charlie Misner both decided now is the time for us to consider doing seriously experiments on gravitational waves. And they talked with the other people who were there in Chapel Hill, and they made a plan on how to do this. And that's when they started thinking about the theory behind all of this and how to do it with computers and simulations and things like that. And then Bryce DeWitt at Chapel Hill and other people started to get serious about this. And then in the 1960s, Kep came along and he got really serious about doing it. He was promoting it for years. And so then also back in that time, Joe Weber at the University of Maryland tried to build a small detector and see if he could detect gravitational waves. He didn't actually do it because it wasn't possible, but he didn't know that at the time. He was doing experiments to try to do that. And then that failed. But they continued to do the theory until they figured out this is what we need in order to detect the gravitational waves. And so back in the 70s, they started doing it. So it's been 50 years really since this started being considered. It took a long time.
All right, and we are going to end it there. Thank you very much, Ron. Wonderful.
Thanks to Steve.
And Steve and everybody for your questions.